And thank you everyone for attending my lecture again. So I guess for my last lecture, let me start by just give you a quick summaries of what I've been looking at, and hopefully it will give you a better picture of what I've been talking about. So, so the main focus of my talk was on two problems. One is the interpolation problems, and as I mentioned in my first lectures, if one is interested in when a set of point or a set of fed points with the same multiplicity has maximal Hilbert functions, then that's is a very difficult problems, even in a case where the multiplicity are all two. That's a major theorem of Alexander and Hershkovich. And the Alexander and Hershkovich, or the study of the situations, is very much related to the study of secant varieties and secant variety of Veronese variety, particularly, and also the Waring's problems, which I didn't have a chance to talk about. On the other hand, if one is more interested in the initial degree of the ideals of a collection of fed points, meaning instead of looking at when the Hilbert function is maximal, we want to look at when is the first place that the Hilbert function is not the same as the Hilbert function of the ring, which is the obvious one. Then in this case, we are interested in the initial degree of the M symbolic power, sorry, this should be x, and the M symbolic power of Ix, which is the same as I of Y. And in this directions, there are a number of important conjectures. Nagata's conjecture, of course, is the most famous one. And then there's Chunovsky and Imai's conjecture, which is a generalization of Chunovsky's conjecture. In the past, before we get into this conjecture or these problems, there are a lot of different results, particularly the most recent result about Fowley, Montero, and C. In 2018, they started to use the technique of specializations to prove that Chunovsky and Imai's conjecture are true for very general set of points. And our goal is to get rid of this very condition. So just look at the general set of point. And in order to do that, what we were looking at is to, instead of considering another problem, which is also very, very well studied in algebra, at least in the commutative algebra community, and that's the containment of powers of ideals, particularly the containments between symbolic and ordinary powers of ideals. For this conjecture, specifically, one does not need the full statement of the containments. We really need this containment for power R big enough, or for infinitely many values of the power R. So we are interested in the stable containments. Now, as before, if we try to apply specialization, because we are proving a statement that involves infinitely many values of the powers. So if we apply specialization, that would mean we have to apply specialization once for every power. And every time we apply specializations, whatever statements we have from the generic set of points go down to the specialized set of points, it only holds in an open subset of the parameter space. And so that means for infinitely many powers, you would have to take the intersections of infinitely many open subset. And that's why you run into the situation where you have to consider very general set of points. So to overcome that obstacle, so that we can prove the conjecture for just general set of points, meaning finding just one open subset, as I said last time, there are two different possibilities. One is we try to prove that there's one open subset that works for all powers, or, which seems to be a very difficult thing to do, or we can just apply specialization once for just one powers and somehow try to get what we want. And this is what we what we did. So what we did was we look at the generic set of points, And then we establish one containment, or inequalities, if we're interested in inequalities, for this generic set of points. And then we apply one specialization, just one power. And then we get one containment for the specialized set of points on one open subset. And then we prove a theorem that is called one containment implies stable containment, meaning in order to get these stable containments, all you need is just one containment. Right? So this is the content of my lecture today. I'm going to talk about how one look at one containment for generic set of points and how we get one containment implies stable containment. Okay. So this is my fourth lecture. We're talking about containment and inequality for general set of points. And so the first section is one containment imply stable containment. That's actually the most important contribution that we have toward these problems. The rest are somewhat known or have been applied before by other authors. So what we did was to prove the following theorem. This is 4.1. So this is a theorem by Bissiou, Griffo, myself, and Nguyen in 2021. We proved that if, so again, just let I be a radical ideal of big height H in the polynomial ring R, and let me just once again saying that this polynomial ring corresponds to the n-dimensional projective space. If there exists a constant C, just one value, such that we have the containment that I of HC minus H imply and contain in M to the power R times H minus 1 and I C. So R is now replaced by C. Some I to the C. So if there's, meaning this, if you look at this, this is exactly, or not exactly, the power here is slightly different from the Haber and Hudicki containment. Haber and Hudicki containment is just this power without this H, right? The statement is for all sufficiently large power R. So what we're saying is that if there's one power C so that this containment holds, then the same containments, but now we have H, we have R instead. Hold for all R big enough. So of course, having a smaller power here means that you have a bigger ideal. So if this is contained in here, then the conjecture power would be contained in this on the right hand side as well. So the difficulty in this problem is, in fact, at the beginning we had a hard time just writing the proving the statement without this minus H. Just assuming that the conjecture containment holds for one value C, then it should hold for stable or large enough values R. We actually had a hard time proving that. And then we found out that if we include a negative H here, then things actually works out. So let me give you maybe an example here. Let's see what this will give us. So maybe I'll recall the Fermat's configurations in P2. So maybe I'll draw that for you again. So this is, excuse me. This is an ideal. Let me even write. So R is C, X, Y, Z, and I is just X, Y to the n minus Z to the n, Y, Z to the n minus X to the n, and Z, X to the n minus Y to the n. And so what we know about this is that this is a counterexample to the Harburn containments. However, we can test that if you look at I to the power symbolic 10th power, right, is contained in m to the 5th times I to the 5th. Right? So there are different ways of testing this. Either you can just use Macaulay 2 and test it directly because you know what the ideal is, or you can do some argument. So this is one containment, right? And this is exactly of the form that we're going to see here because 10 is just 2 times 5 minus 2. That's not true. 6, sorry. 2 times 6 minus 2. So this should be 6. And so by this theorem, this implies that I to the 2r minus 2 is contained in m to the r, I to the r for all r big enough. And this establishes the stable Harburn. Because stable Harburn basically say that you have I, the 2r minus 1 should be inside m to the r, I to the r. And of course, I to the 2r minus 1 is already inside I to the 2r minus 2. So we actually prove something slightly stronger than stable Harburn conjecture. So what this is saying is, even though the Fermat configuration give us a counterexample to Harburn containments, but it doesn't give us a counterexample to the stable Harburn containment. So sometimes the containment might fail for the first few values, but when you go for large enough powers, it still holds. Another example is, again, the second example that I mentioned to you. It's this one right here. So this is 19, the ideal of 19 triple point, which are intersections of 12 lines. Okay. And what we also know is that this is a counterexample to this containment. However, we can verify here that I to the symbolic 8th power is contained in m to the 5th, I to the 5th. Once again, you can do some direct argument, or you can just verify that with Macaulay 2. So by the one containment implies stable containment, we know that I to the 2r minus 2 is contained in m to the r, I to the r for all r big enough. So once again, this is a counterexample to Harburn containment for small values of r, but it's not a counterexample to the stable Harburn containment. Still satisfy stable Harburn containment.
Both the cases, the height is 2.
Yes, yeah. So they are point in P2, right? So height is 2. So of course, so let me also recall that the general form of the Harburn, let me just put abbreviation here, Harburn-Hunicke conjecture, basically say that we should have I to the r t minus h plus 1 contains in m to the r h minus 1, I to the t, and to the power r. So we were actually hoping to get some sort of similar statement like this. We were hoping to say that, well, if we can prove this containment, or maybe some slight modifications of this containment for one specific value c here, then we would have this containment for all big enough value R. Unfortunately, that proves to be very difficult. So what we could prove was slightly weaker. We need a stronger statement to imply the stable statements. Okay, so let me put down another theorem here. So this is 4.1.2. So this is also again by Bisu, Gufo, myself, and Win in 2022. So what we proved was that again assume for the same ideal I, if there exists a value C such that the containment we need is the following: I to the power C times T plus H minus 1. So that looks very similar to this. However, we need to drop the power by H minus 1. So minus H plus 1. If that is contained in what we need, right? M to the C H minus 1, I to the T C. So it's not the same as that. It's slightly stronger because the power is smaller. Then the desired containment, so R to the T plus H minus 1 is contained in R, M to the R minus H minus 1, I to the T to the power R. And we couldn't even prove this for all R big enough. We can only prove it for infinitely many holes for infinitely many values of R. But that's enough to establish the Demai's conjecture. Right. So it boils down to, so maybe I will state it here. So thanks to this one containment implies stable containment, what we were able to establish was Chudnovsky or containments and inequalities that we wanted for general set of point. And so, theorem, maybe I'll put the theorem here. So 4.2.1, this is again by the same group of people. What we prove is that the stable Harborn conjecture holds for a set of general point, any set of general point. And so let me give you a very brief sketch of the proof. So first, the stable Harborn conjecture or the Harborn containments as the following. So we, again, as I said, we moved to the generic set of point, right? So we established the containment. We just established the containment. And this is now we're looking at not just I, but IZ, which is the ideal of the generic set of point to n C minus n plus 1 contained in M and IZ to the power C for some value C, where IZ is the defining ideal of the generic set of point. In this space when we enlarge the ring, the field. So that's the first step. And in fact, we proved that actually this statement is true for all big enough values C. But all we need is just one value C, and then you use specializations. Remember that we just need one value C to get an open subset U in the parameter space, such that for all A inside U, we have the containment that I of A, maybe I should have written more carefully. So this is I of XZ, not I of Z. So I of XZ, the defining ideal of XZ. So here should be the defining ideal of XA to the power NC minus N plus 1, containing M to the power I XA to the power C. And so basically that's that this is saying that this containment is true for one general set, for a general set of points. And then we use one containment implies stable result for applying to this containment to get the stable containment, to show that. For all A inside just one open subsets, I of XA, which is the specialized set of point, and R minus N plus 1 is contained in M I XA for all R big enough. So, so this particularly implies that this guy has what we call expected resurgence. So I'm not going to talk about this, but anyway, from here we already know that it's the theorem holds, right? So so that's the idea of proving a stable containments, or and of course for stable containment you have Dimai and Chinovsky. For example, the next one would be theorem. Maybe I put out a theorem here just to. So maybe I'll put down a, yeah, so maybe suppose, so this is the stable Haber-Hunicke, that n is bigger than or equal to 3, and s is bigger than or equal to 4 to the n, then the stable Haber-Hunicke conjecture hold for a general set, for a set of S general point in Pn. And so let me again sketch the proof, and the idea is very much the same. So first we move to the generic set of points, we establish whatever we want for the generic set of points, and then we specialize once. Right? So here we're going to establish, let's say this containments I of xz to the power nc minus n. So remember that the stable Haber-Hunicke conjecture said that this should be nc, right? But the one containment imply all containments or stable containment that we have has to have this negative n. So that's why there's this statement here. Containing m of I of xz to the power c for some value C. So once again, in this case, we actually prove that it's true for all C begin F, and then use specializations. Once to get I of X to NC minus N contained in M I, wait, sorry, this is be C. The statement should be C N minus 1. So this should be the same, C N minus 1 I of X for a general center point. And then we use, again, one implies stable results to get the same containments. I of X to N R minus N contained in M R N minus 1. There should be a C here, sorry. I of X to the power R for all big and F. And remember that this contains I of N R. So that established stable Harburg-Hundicke containments. So in both of these results,
excuse me. Yeah.
Yes, go ahead.
Yeah. Regarding to the previous proof, when you was using the specialization, you was using that result that there exists some point A in the open set U. And when you are using in the second time specialization, so is there any importance of mentioning a particular point when we are proving these kind of inequality by using the specialization?
Oh, you mean the difference between my expression here and my expression here, right? You're saying that?
Yeah.
There's no. I'm just lazy, so here I write in a shorthand. So the right. I mean, as I said before, right? When you have XZ being the generic set of point, every time you specialize, meaning you replace Z by some A. And then,
okay.
Yeah, and then so you get XA. And of course, you also know that every set of point in Pn comes in this way. For every set of point in Pn, there's some A such that you specialize XZ to A, you get the same, you get a given set of point.
Okay.
And so if you can prove that there's an open dense subset in the parameter space, so that some statement is true for this A inside that open dense subset, that means you are proving the statement for a general set of point.
And when we are just curious again, forgive me for this naive question. When we are writing this inequality follows from the specialization, that means we are considering about the original ideal, or we are considering the ideal associated to the affine variety case?
No, we are considering the ideal. So when I write I of XA, right, you mean this statement?
Yeah.
This is the defining ideal of the set of point XA inside the projective space.
Inside the
projective space. Yeah, so my specialization is like this, right? So specialization, maybe I'll write here. Specializations is I have P ends over the the field extension. And then I have this set of point XZ, that's just one fixed set of point in my projective space. And I specialize now to P end over C by just replacing Z with A. I get this is a set of point in here.
Okay.
Right. Okay. And so this is a subvariety of P end, and I of XA is just the defining ideal of this subvariety inside this projective space.
Oh, thank you.
Yes. Sorry, I didn't make myself clear. Okay, so if you look at both of these proof, these two steps are kind of straightforward because follow from specializations, and then this guy followed from the one containments implies stable containments. So what are the difficulties? Why in this theorem, for example, we need this condition that S has to be at least 4 to the power n? It lies in the first step. In any case, even if you reduce to the generic setup point, there's just one generic setup point, we still have to establish a very specific containment. And we have to find out which value C this containment would hold. And in general, that's not very easy. Our method at least is very combinatorial. Actually, this is a very new kind of a combinatorial formula kind of thing. And to prove that, we need this condition because it's more or less a counting kind of arguments. On the other hand, here, for example, in order to, again, to get the same result, the last two steps are straightforward specializations. One containment implies stable containment. So the theorem boils down to establishing one containment for the generic setup point. But this containment is actually, one can prove directly for any setup point, for any number of points. Or actually it's followed from previous result by Tulane and C. On the other hand, so you see the difference between this guy and this guy here is this extra power of M, and of course the power is slightly different. But the extra power of M is the difficulties that creates problem for us, and that's why when we want to get this extra power of M, we have to have enough points so that we can extract the power of M, the power of the maximum ideal out. So that's the difficulties. Okay, so maybe I'll move on and give you maybe one more theorem here. So this is so far I've only talked about Chudnovsky's conjecture, right? So these statements here basically give me Chudnovsky. And so for DeMayi, what we have to prove, as I said, is slightly different because for DeMayi, we do not have the results that one containment implies stable containments. So what we need to prove is, again, so maybe I'll say the result first. So let n be at least 3. T is a positive integers, and then DeMayi conjecture holds for a set of S at least 2t plus 2 to the power n general point in Pn. And so let me just say the proof once again, we have to, the first step is to focus to the generic set of points, try to establish whatever containment or inequality that you would like to have for the generic set of point. So for us, because of the image conjecture, you need a slightly stronger containment. So we have to establish the containments. Maybe I'll write out right here. I of xz to the power c t plus n minus 1 minus n plus 1 contained in m c n minus 1 I to the power t to the power c for some value c. For some value c. And then we use specializations. So once again, I should have written that using specialization, there's an open dense subset in the parameter space, so that if you look at specialized points with your parameter inside that open dense subset, then you have the containment. But for short, I'm just writing down the containment and say that it's true for a general set of point. Is specialization to get the containment that I of x c t plus n minus 1 minus n plus 1 inside m c n minus 1 I of x to the power t to the power c. for a general center point X inside Pn, right? And then now we have to use second theorem, right? So now we use not the one containment implies stable containment, but this one. Here you have a stronger containment that implies a weaker containment for infinitely many values of. Right? So use known results. So known results to get I of x to the power r t plus n minus 1 containing m to the r n minus 1 ix to the power t to the power r for infinitely many values r. And this basically gives us the Demey's conjecture, right? Demey. Because again, for these two conjecture, all we need is the containment for infinitely many values of the power. So, a couple of lectures again. I think somebody asked me, what happened if you move beyond points, right? Are there any similar results for ideals of any subvariety or any projective variety of any dimension of any big kinds, right? So let me spend my remaining time to talk about containments beyond maybe containment and inequalities.
Excuse me, Professor Hao?
Yes.
Yeah, I'm just curious about this C. When you was trying to establish that inequality, usually the C is very, very large most of the time.
Yeah, so in most of the time that when we establish, so remember that here we only need this containment is true for one value C, but in most of the time we actually prove this this containment for let's see, in the other case in the other cases we prove the containment for all C big enough. And this case, I think in this case we actually exhibit what this value C should be. Yeah. So again, and exactly because of these steps where you have to find one value C that makes this containment hold, you need these conditions, right? So again, there's some counting argument and making use of what is already known about the Nagata's conjecture. So that's the idea behind the first step here.
Okay, thank you.
You're welcome. Okay, so let's talk about containment and inequality beyond points. So as I said before, when you look at ideals of any projective variety, your big high is no longer n. So we don't expect the same kind of containments or inequality where you still have n here, right? So you have to replace by something else, and because there's been containment results using big height, so it makes sense to think about this same kind of containment replacing this n by big height, right? So the first questions I'm going to state here is that let I be a radical homogeneous ideal in R of big height H. Does the containment I to the R T plus H minus 1 contingent M to the R H minus 1 I to the T or R holds for R large enough. So you see that it's very much the same as this containment, except now instead of having n, we just have the big high h. So this is a generalization of Habermas or the stable Habermas-Hunicke containments. And here, instead of looking at radical homogeneous ideal in a polynomial ring, you can also state the same question for any radical ideals in any regular local ring. Right? So if you are more comfortable with local rings, you can also state the question in that context. And then questions, or you can also ask, or for all R and T, maybe it's true, maybe it's not, right? Or you can also ask, what happened to equality that looks like Demai's or Chudnovsky's equalities? So let I be as before.
Sorry, excuse me.
Yes.
Yeah. So here, okay, R and T can be any natural number, or for all possible.
Yeah. So I just put this question here. We don't know what should be the correct statement, right? You can ask this question: is excuse me, is this containment true for all R and T? Right? You can ask the same question. There might be, it might be true, it might not be true. There might be counterexample. If they're counterexample, then you can rephrase the question and ask, well, is it true for all T, but for R big enough, right? To avoid, you know, like particular counterexample with for small values of the powers, right? So for now, I'm going to ask this question because I don't have any counterexample, right? But generally, I do expect counterexample. So I think the more I mean the higher possibility is that this statement will be true for R large enough. Okay, so this question that the inequalities. So remember that our initial inequalities is alpha of I to the power m divided by m bigger than or equal to alpha of I to the power t plus h minus 1. This is Demai's conjecture. Instead of having n, you now have h. So t plus h minus 1. Does this hold for all maybe R, m, and t inside it, right? So those are the two questions for any class of radical ideals that you feel comfortable working with. So for example, in general, when one talk about ideals, especially coming from geometric context, the first example that people usually test is determinant of ideals. And in fact, we do prove that determinant of ideals satisfy this. So let me put an example here. So for a fixed, maybe for fixed integer, positive integer t less than or equal to the mean of p and q, let X be a P by Q matrix of indeterminates. And let I equal to IT of X be the ideal of T minus of X. So you take all T by T submatrices in X and you take determinants that will generate an ideal, and that's called a T minus of X. then it's not very hard to see I is a prime ideals and has height. In this case, heights and big heights are the same, given by P minus T plus 1. So this is a famous result. If you work with determinant of ideals, you will know this. And so what we can do is we can verify that for all R, T, and C. Maybe I should use T. I already have T here, so maybe L and C bigger than or equal to 1. We have I to the R, L plus H minus 1 contained in M R H minus 1, I to the power L to the power R. So this is exactly what we're looking for, right? And it's true for determinantal ideals of a generic matrix. You can also, instead of looking at a generic matrix, you can also talk about ideals of symmetric matrix of indeterminates, right? So maybe, again, or maybe for T less than or equal to P, let Y be a P by P, so it's a square matrix and a symmetric matrix of indeterminates. And let I be the ideal of T minus of Y. Then in this case, one also knows that I is prime. Again, this is a famous results of height H equal to P minus T plus 2, P minus T plus 1 divided by 2. And once again, for all R, L, and C, there's no C, I think. Sorry, in my statement, there's no C. I have a more general statement that has C, but here I don't have C. So let's just forget about C. Inside and we have the expected containment. Right. And then I think that's it. So one can also talk about, one can also prove the same results for ideals of Fafavian of a skew symmetric matrix instead of symmetric matrix of indeterminates. And you get the same kind of containments. One can also talk about the ideals of star configurations, and you will get the same containments. I think it's a good time for me to, oh, I think I still have time, right? I'm sorry.
Yeah, just one question. So the same thing is true for the toric ideal?
Not that I know of. So I suspect that is true, but let me maybe write here. So what I also know is that the same thing is true for the following. Same conclusions holds for, so let's see, you have ideals of let's say Fafavian of a skew symmetric matrix of indeterminates. So let me explain this a little bit. So here for symmetric matrix of indeterminates, you really want that Yij is the same as Yji, right? So that's what it means by symmetric. For skew symmetric, you want Zij to be negative of Zji, and particularly the diagonal entries on the diagonal will be 0. And you want the size to be even, and then you take any even minors of the matrix, that even minors, and then you take the square root of that even minors, right? The square root will generate this ideal, which we call the Fabian ideal of this matrix. It's also true for ideals of star configurations. In PN. Now, let me also say that for star configuration, the classical notion of star configuration is just you take a bunch of hyperplanes that intersect each other nicely, and then you look at the intersection point of these hyperplanes. However, one can, instead of looking at hyperplanes, also look at hypersurfaces. So you take a bunch of hypersurfaces, again, they intersect each other nicely in the sense that if you take a sequence of them, short enough sequence of them, they always form a regular sequence, right? So, and then you take the points of intersection of these hypersurfaces. That's from what we call the still the star configuration of hypersurfaces. And the same conclusion, the same kind of inequality is going to hold for a star configurations.
Yeah, one more thing. Can you return to your question number 4.3.2?
Number 4.3.2, yes.
Wasn't here M to be approaches to infinity? On the left hand side.
So whether or not you put this, or you can also put instead of putting this, you can also put alpha hat, right?
Yeah, exactly.
It's the same. The conjecture. So the conjecture that this is true for all M is the same as saying that alpha hat is at least this. It's equivalent. Because we know that alpha hat is the limits of the left hand side, right? But we also know that alpha hat is the infimum of the left hand side.
Okay. Now I got
right.
it.
Yeah.
Yeah.
So if alpha hat is bigger than this, then everything else is already bigger than this.
Thank you.
You're welcome. So I think that's it for me. I'm going to finish my lecture here. Once again, allow me to thank the organizers for inviting me to present my work here. It's my pleasure and my honor. And thank you again for attending my lectures. And now I'm open for questions if you have any.
Thank you, Professor Ha. Is there any question from the audience? Maybe in the chat box, is there something? Thank you everyone for, okay. Is there someone with question or probably with remark? Yeah, Hassan. Okay, if this is the case, now let's thank Professor Ha. This is a wonderful series of lecture you have delivered on containment problem. In fact, definitely we have seen the containment, but mostly in the monomial cases, and particularly your paper, which appear with Boki, Uwe Najal, and then many, particularly the case of scare-free monomial case, where you gave a formulation for computing the Waldschmidt constant. I was just curious to ask one question regarding to that particular paper. Is there any interest of finding certain classes of ideals coming from a particular graph, which is giving, definitely your result is giving a bound for the Wald-Schmidt constant, but still there is some interest in refining that particular bound for particular classes of ideals by using the same result.
Yes, the answer is yes. The question about the Wald-Schmidt constant is always a difficult question, even for monomial ideals. It's not very easy to compute the Wald-Schmidt constants. So because we prove the full containments, I think we prove even more general version of that containment for square-free monomial ideals. So we know that this kind of inequalities would hold for the square-free monomial ideals. But you know how, of course, because this is an equality, so one can always say, well, can we improve the right-hand side? So that's a very good question, which I don't know the answer of. And go ahead. Sorry.
Yeah. So the bound you have given by using the linear programming was it the sharp bound? I was just using the same result to obtain bounds for different classes of ideal by using the graph.
Using the same result. Yeah, so that's another part of the containment ideals that initially I was hoping to be able to talk about. So the same kind of containment, right? Remember here I present to you how to use containment of ideals to investigate the interpolation problems, particularly the Chudnovsky and Imai's conjecture. There's another way of looking at containments of ideals and its application in integer linear programming. So in fact, I wrote a paper with Chung where we discuss how containment of powers of ideal correspond to gap estimate between optimal solutions and integral optimal solution to a linear programming problems. And now there are a number of containment that have been established for square-free monomial ideals that directly translate into this gap estimates for linear programming problems. So those will give us new bounds. And then there's also known results in linear programming where they actually talk about gaps between optimal solutions. We can also translate that back to new containment of power of ideals. So so far, at least in my paper with Chung, we only talk about direct translation of known results in algebra. What does it give us in terms of linear programming, and known results in linear programming? What does it give us in algebra? There are a lot to explore. We haven't talked about whether or not we can improve the known results. For example, can we improve the containments by looking for better bound from the linear programming problems, or can we improve the known bounds or the gap estimates in the linear programming problem by obtaining better containment results? So that is something that we haven't looked at, and I think it's worth very much to explore.
Yeah, thank you very much. Thank you. These 4 lectures were full of information, and definitely there are few students who already have a little bit background on algebraic geometry. And definitely the techniques which is being used here, that gives them 4 ahead problems working, who are looking for problems for the projects working in the algebraic geometry. I think containment problem always hold one of the central problem in the area of commutative algebra and algebraic geometry. Thank you very much, Taiha, for introducing this particular problem in front of this curious audience. Let's give an applause to Professor.
Thank you for having me.
And now I request you to please stop the screen share so that we can view you. And I request all the participants to please gather here so that we can have a group photo with Professor Taiha and have some ceremonial closing of his lectures. Just wait for a while.
I have a question from Professor Taiha.
Okay, go ahead, please.
Actually, this is a question from his yesterday lecture. In the yesterday, Professor Hall defined a theorem, that is theorem 3.17, given by Krull, and
Yes.
it's given two of the main results on pi survey, that is pi survey of I intersection j is equal to the pi survey of I intersection pi sub intersection j. This is basically I and j are the two ideals.
Right. Yes. So I and j in this case would be ideals, but inside the polynomial ring with variable x0 to xn, but coefficients are rational functions in the new indeterminate zij.
Actually, I have a question whether we could connect this result and whether we can create the independency of two ideals. Independency of two ideal mean when we apply pi of I intersection j, could we generate the result pi of I intersection pi of I into pi of j? That is basically the result of independency of two ideals.
You mean the question is whether or not this open dense subsets for this equality to happen is dependent of the ideals, of the choices of the ideals? Is that the question?
आप लोग भी प्लीज सेंटर में आ जाएं. Come on.
Sorry, I couldn't hear the question.
हाँ, आजेगा. There is no issue. आप लोग प्लीज बाकी इधर आगे भी इधर आए प्लीज थोड़ा सा और प्लीज आप चलो वो स्टैंडिंग ना आजे.
You, Professor How?
Hello?
Yeah. Actually, my question is, could we define the independency of two ideals? And the main idea behind the independency of two ideals, that is pi of I intersection j, which is equal to the pi of I into pi of j.
Yeah.
Could we create this result?
So maybe it's better if I share the screen so that I know if we are talking about the same thing. Is it okay? So are you talking about this this containment this result here?
This is yes. This is the result basically. Basically,
yes,
my first result pi of I intersection j, which is equal to the pi of I intersection pi of j. Could we replace this result pi of I intersection j, which is equal to the pi of I into pi of j, so that we can create the independency, the two ideals become the independent ideal.
Oh, so I haven't thought about it. I mean, what I do know is one containment is always true for any ideal. So I think if I remember correctly, I think this containment is always true. And then for this containment, you need A to be inside some open subset. And this open subset depends on the choice, of course, depends on I and J. Now, I don't know what happens if I and J's are independent. For example, if you're talking about ideals involving different variables, I don't know in that case if you can check this to be the whole space. That I don't know. But it could possibly be, yeah. Is that your question?
Yeah, I got it. Thank you.
Yeah. So let me stop sharing.
डॉक्टर इमरान कि हम रिफ्रेशमेंट के लिए मूव कर जाएंगे अभी वेट करें पिक्चर का आप प्लीज बता दें
Professor Ha, can you hear me?
Yes, I can.
Yeah, sorry. In fact, there is an insignia. Can you see that? Now. Okay, there is this particular insignia and souvenir from our side. So there is your picture inside.
Oh.
We are going
Thank you.
to send you via post very soon. You will receive it.
Oh,
Okay.
thank you so much.
As just a token of thanks for your lectures and staying connected with CIMPA School at LUMS. And we are hoping that this is unfortunate we could not have you here. And we wish you a quick recovery. And we wish that we will meet sometime somewhere in maybe in Pakistan very soon, or maybe somewhere else.
Yes, thank you so much.
Thank you from my side. Thank you from my side.
Only some words in the name of CIMPA, as a representative of CIMPA. Thank you for your lectures and the effort you have made to give the lectures at such a strange times, even at 3 in the morning. Thank you very much.
Thank you for organizing such a nice school and for giving me the opportunity to talk about my research here.
It's been a pleasure.
Yeah. Thank you, everyone.
I think Asian tradition. It's also not in India. Not in India. Even in Lahore, I think so. It's more in the fashion trends are here. Yeah. The fashion trends here in Lahore you can find.